Hello physics lovers, welcome to the lecture. In this video, we'll explore one of the key concepts in physics, namely the force, and how numerous types of forces that we experience in our day-to-day life really boils down to just four fundamental types of forces. Not a single day passes in our life without coming face to face with one or the other kind of force. You know, if someone throws something at us, we experience some impact or force. If we need to push our car in the morning to get it started, we know we need to apply some force. Thus, we get to deal with force in our day-to-day life in various forms. For example, frictional force, electrical force, spring force, or tension force, air resistance, etc. So what is really this thing that we call force? It was Sir Isaac Newton who laid foundation to our current understanding of what we call today as force. In fact, the concept of energy evolved much later in the 19th century. Till then there was no notion of something called energy. The legendary Greek philosopher Aristotle, who lived almost 2300 years before, thought force is something which causes unnatural movements or violent movements, as he called. What's unnatural movements? Natural movements are those involved with free falls, say a mango falling from the mango tree or something kept on the table falling down. And unnatural movements or violent movements are those where, like, we push a book along the table, or we push our bike, or pushing a chair along the floor, etc. As per the modern definition of force as laid out by Newton, force is a push or pull upon an object resulting from the object's interaction with another object. When there is an interaction between two objects, there is a force experienced on each of the objects. And when the interaction ceases, there is no force any longer experienced on the objects. Please note that the interaction doesn't necessarily need to be through physical contact. It can be contactless, or what we call as action at a distance type of force. For example, magnetic forces are contactless or action at a distance type of force. Such forces, even when the objects are not in physical contact, are able to exert push or pull even while they are at a distance apart. So the key is, force is the result of interaction between the objects. It doesn't exist independently if there is no interaction. That is, we need at least two objects, one to exert force and the other to experience the force. So, to be precise, it's not the force that acts on the object, it is one object acting on the other object. And as a result, the object experiences what we call force. So, force is the result of this interaction. So, if there is no object exerting force on you, then well, there isn't any force acting on you. Every single such interactions happening in the universe can be broken down and described by four fundamental types of interactions or forces, namely gravitational force, electromagnetic force, strong nuclear force, and weak nuclear force. These four fundamental forces. So these are called fundamental forces in nature. So all the forces that we experience in our day-to-day life can be broken down to one of these four fundamental forces. Though the relationship is not straightforward, rather it is pretty complex. Okay, wait a second. Before I move ahead, I said right now four fundamental forces. Should I say three? Why? Well, actually, the weak nuclear force and electromagnetic force turn to be one and the same. Electromagnetic force and weak nuclear force are one and the same. So, in that sense, there are three fundamental forces. Okay, hold on. I would rather say two. Okay, I promise I will not reduce it further. But why 2? Well, blame it on great Einstein. As per Einstein, as proposed in his general relativity, gravity is not really a force. It's rather an effect of space-time curvature created by these massive objects out there in the universe. Okay, we'll come to that later in the lecture. But one of the very exciting quests in physics is to unify all these fundamental forces into one single force, or in other words, to get a one single set of equations that would describe everything happening in the universe. So that's one of the very exciting endeavor happening in the world of physics. Okay, so let's come back to our 4 fundamental forces. Let's not jump the gun too soon. For gravity, currently we will stand by Newton, his theory of gravity. So out of these 4 fundamental forces, which one you think is the strongest of the forces? Which is the strongest force? Did you say gravity? I guess most of the people say a thing, it's gravity. Naturally, because we see every object going up come back to the earth with a thud. So it must be pretty strong. But sorry, you got it wrong. In terms of magnitude, gravity is the weakest among the 4. Not just slightly weaker, but enormously, tremendously weak compared to other forces. So if we arrange these fundamental forces from strongest to weakest, it would be first strong nuclear force, then electromagnetic force, then weak nuclear force, and the last gravitational force. For example, if you keep 2 particles close by and assume the strong nuclear force between these particles is say 1 unit, then the gravitational force between these particles would be 1 out of 1, 0, 0, 0, 0, 0, 0, put 39 zeros in there. Just 1 out of that big a number, which means it is really a tiny fraction of the strong nuclear force, which is 1. So gravitational force is that weak or that small. In fact, electromagnetic force would be just 1 by 100. That is just 100 times smaller than the strong nuclear force. If so, how come we experience the gravitational force so predominantly, so profoundly, and how gravity dominates the universe, especially the cosmic world? So let's dig a little deeper to understand and unravel this mystery. So what is the gravity or gravitational force? Gravitational force is the attraction between any 2 objects in the universe having mass. Gravity is a universal force every object exerts on every other object in the universe by virtue of their mass. Okay, then what is mass? So we know that there are so many things that we see around us, the real objects. So mass is nothing but a measure of how much stuff or matter is in there in one object. It is defined by Newton as the force required to move an object from rest or to accelerate an object, overcoming its inertia. More the inertia, more force is required to overcome the inertia and accelerate that object. This mass is called inertial mass. Newton has also defined another kind of mass known as gravitational mass. Gravitational mass is defined as the amount of force an object exerts on other objects. Both these masses, inertial mass and gravitational mass, are equivalent or they are same. So gravitational force is the attractive force that an object exerts on other masses by virtue of their mass. Bigger the mass, bigger the gravitational force. Gravitational force is always of attraction. There is no repulsion. Why? Because there is only positive mass. There is nothing called negative mass. That means for huge objects, the gravitation force adds up and it becomes really a dominant force. So now you know it is a huge mass of the earth that makes the gravitational force exerted on the objects on earth very high. Gravity is the force that keeps moon revolving around the earth. So is earth revolving around the sun. And pretty much the force behind the formation of all the planets, stars, galaxies and the entire universe. So if the objects are tiny, small little ones, small little particles, then obviously the gravitational force will be negligible because the mass is very, very little. Thus, the gravitational force is very dominant in the macroscopic world, in the bigger world or in the astronomical world. It is very negligible in the microscopic world or atomic or subatomic world because the mass of the particles involved are very minuscule. Now the other aspect of the gravitational force is that its range is infinite. Though the intensity of the force will keep diminishing as the distance between the objects increases, actually in reverse proportion to the square of the distance between the objects. But the range is infinite. So even if you keep two objects far away, there will be still some effect or impact of gravity between them. So how is this gravitational force transmitted? This force is transmitted via gravitational fields. I had mentioned just a while ago that the gravitational force is not really a force according to Einstein. In his general relativity, what Einstein proposed is gravity is not really a pull force or a force of attraction. What he proposed or postulated is, which is verified to be true with numerous experimental observations. So what he said is, gravity is not really a force exerted by an object, but it is the impact of curvature of the space-time an object creates because of its mass. What that means? So let's consider a plane, a surface as space for now. Now on that plane surface, you keep, let's place our sun in there, the huge mass. What would happen? The plane surface will have a dip because of the mass of the sun. So there is a curvature on the plane or on this space. Now near that curvature, if you place our tiny earth, what would happen? It will start revolving along the curve. So the whole gravity is not that sun is attracting earth, but it's earth responding to the curvature in the space created by the sun. This is what Einstein's general relativity postulates or suggests. So what Einstein said is the rotation by all the celestial bodies, planets and stars, all because of the curvature in the space-time. Okay, we will not go into the detail of general relativity. We will explore the theory of general relativity in probably another lecture. Now further, if we enter the world of quantum physics, then both these theories go for a toss, because in the world of quantum physics, the gravitational force is transmitted through tiny little particles known as force-carrying particles. According to quantum field theory, gravitational force is because of exchange of tiny force particles called graviton. Again, we will reserve the topic of the quantum theory for another separate lecture. So now let's come back to next in the list of four fundamental forces. That's electromagnetic force. Electromagnetism is the interaction between the particles carrying electric charge. This is a much stronger force compared to the gravitational force, but is experienced obviously between only charged particles. nature of the electromagnetic force between the particle would be that of attraction if the charge of two particles are of different sign. One is positive and one is negative. And the force would be that of repulsion if both the particles carry the same charge. If both of them carry positive charges or negative charges, the force would be that of repulsion. So, the electromagnetic force in big huge bodies, actually they cancel out each other because there are both positively charged and negatively charged particles, and the force cancel each other. So as we know, since the charge comes in two signs, positive and negative, the forces can cancel each other. While in case of gravitational force, since there is only positive mass, there is no negative mass, the force always adds up and hence it becomes predominant than electromagnetic force, though the electromagnetic force is much stronger than gravity when it comes to huge objects like planets, stars and galaxies in the astronomical world. However, on the scale of atoms and molecules, it's the electromagnetic force that is predominant. This is the force which is in action in most of the processes and activities that we encounter in our day-to-day life, including all of the chemical reactions, biological reactions, everything. The electromagnetic force, similar to gravitational force, also is a long-range force. That is, like, even if you keep the objects, the charged particles at a fair distance, they would still exert a reasonably good force. The electromagnetic force consists of two components, obvious from its name. One is electrical component and the other is magnetic component. When the charged particle is stationary, not moving, electrical force is in action. But as the charged particles start moving, it begins to generate magnetic field and thus exert magnetic force. Since atom consists of both positively charged and negatively charged particles, electromagnetic force is predominant at the atomic level. In fact, it is the electromagnetic force that is responsible for the structure of the atom and the molecule and holding together everything in the universe. In fact, if there is no electromagnetic force, or if the electromagnetic force was not so much stronger than the gravity, this universe would have fallen apart. It's the electromagnetic force which is the underlying force behind pretty much most kind of forces that we experience in our life, like say tension force, spring force, friction, elasticity, the drag when an airplane flies in the air, the normal force, so on. For example, the normal force that keeps, say, a glass on top of a table without the gravity pulling it down is because of the electrons in the atoms of the table repelling the electrons in the atoms of the glass. It's that strong. If not for the electromagnetic force, the glass kept on the table would have fallen down. We ourselves would have crumbled on our own weight, but for the net electromagnetic force between the charged particles in our body. It's the electromagnetic force that is holding us intact against the Earth's gravity. But the phenomenon of electricity and magnetism were actually considered as separate, unrelated things almost until 1820. Electricity was this hissing and crackling sound associated with batteries. Magnetism was, on the other hand, this invisible silent force that moved the navigational needles or pulled the iron pieces. These two forces were thought to be completely unrelated, distinct forces until the Danish physicist Hans Christian Ørsted noticed the link. It was during one of his demonstration lectures that he noticed when an electric current was passed through the wire, the compass kept nearby deflected. What he discovered was the phenomenon of moving electricity creating magnetic field, and the exciting fact that the electric force and the magnetic force are linked. It was in fact Ørsted who coined the term electromagnetism. Now this was a puzzle. How come the electricity flowing through a wire just leaps out of the metallic wire and move the needle kept at a distance? Later, Faraday answered that puzzle when he envisioned the magnetic fields traveling in space which carry magnetic force. In fact, Michael Faraday demonstrated years later the opposite phenomenon, that is, a changing magnetic field induced electricity in the metallic wire. And this was the discovery of the century because that was the basis for all the electric engines. In fact, Faraday built the first electric motor as well as first electric generator almost a decade later. In fact, there is a story like this. When the Prime Minister asked Faraday what he can do with this discovery, Faraday replied, "Sir, you can tax it one day." And we know, today we all keep paying the electricity bills. Later in 1860s, another genius named James Clerk Maxwell developed a mathematical framework to describe Faraday's ideas. These are known as Maxwell's equations. And these mathematical equations describe the link between the electric and magnetic forces. Both electric and magnetic forces were proved to be the manifestations of the same physical entity called electromagnetic field. So Maxwell thus unified electricity and magnetism. He also showed that electromagnetic waves can propagate through space as waves, and he calculated the speed of those waves, and astonishingly it turned out to be same as the speed of light. So what he proved was light is an electromagnetic wave. Now coming to the other two forces, namely nuclear forces, these are entirely different in the sense they act inside the nucleus of an atom, and thus we don't deal with them at all in our daily life. So there are two types of nuclear forces, strong nuclear force and weak nuclear force. The strong nuclear force is the one which holds together the particles inside the nucleus of an atom, namely it holds together the protons and neutrons. It also holds together the protons and the neutrons themselves, because the protons and neutrons themselves are composed of more tinier particles called quarks. So as mentioned earlier, strong nuclear force is the strongest of all the fundamental forces. It's more than 100 times compared to the electromagnetic force. But this force is extremely of short range. We saw that both gravity and electromagnetism, it's of infinite range. The reach is infinite range. It can reach distance. But the strong nuclear force, the range is much shorter, to the tune of 10 raised to minus 15 meter. This is almost the diameter of a typical nucleus. So you can imagine the strong nuclear force acts only within the range of a nucleus of an atom. It's not even impacting the electrons which are orbiting outside the nucleus. When it was discovered by Ernest Rutherford that an atom has a central area called nucleus where majority of the mass of the atom is residing, it was evident that a strong attractive force is required to hold all those particles inside the nucleus, because the gravity will not be considerable as the particles are very tiny in size and the gravitational force would be negligible. At that level, the electric force would be more predominant or would be higher. So until the protons were discovered, it was thought that the electromagnetic force, which is holding electrons in the atom, must be responsible for holding the particles together in the nucleus as well. However, in 1920, when Rutherford discovered proton, it was clear that unless there is a strong attractive force to hold the protons together, they will repel each other because protons carry positive charge. So they will repel and fly away, and thus the nucleus will not be stable at all. So one solution was, what was proposed initially, they assumed maybe the nucleus has electrons. So the attractive force between the proton and the electron must be holding them together. But in 1932, this gentleman named James Chadwick discovered neutrons. He discovered that the nucleus of an atom contains a particle called neutron, which is charge neutral. So now it was clear that the nucleus of an atom contains protons which are positively charged and neutrons which are charge neutral. So now again you need a force to hold these protons and the neutrons, everything together. Otherwise protons would repel each other and fly away, making the nucleus unstable. It is then Eugene Wigner proposed that it's not the electromagnetic force that is holding the particles inside the nucleus together, but he suggested instead the nuclear forces. Thus, the strong nuclear force was proposed as the strong attractive force that provides attraction between protons, proton and proton, proton and neutron, as well as neutron and neutron, and thus holding the entire nucleus together. So it is this binding force, the strong nuclear force that holds all the protons, neutrons, everything together, which is released when the nucleus of an atom is split in a process called nuclear fission, the basic process that we use to generate nuclear power. It is the same strong nuclear force, this binding force, that is the source of energy in stars, including our sun. The other nuclear force is what is called weak nuclear force. It's weak only with respect to the strong nuclear force. This is the force behind the phenomenon of radioactivity exhibited by certain elements. Its range is far shorter than the strong nuclear force, to the tune of 10 raised to minus 18 meter, which is in fact much smaller than the diameter of a proton. So you can imagine the weak force with a very tiny range depends completely on physical contact, and this is the force responsible for spontaneous decay of neutrons in the nucleus of an atom into a proton, emitting an electron in the process. This is called beta decay. So the weak nuclear force has a very critical role in the formation of various elements in stars and also in the early phase of our universe when it all started. So we have noticed that the range of the strong nuclear force is around the size of a typical nucleus. So the strong nuclear force will be incredibly strong inside the nucleus, but outside it's nothing. Not even it impacts the electrons, as we said before. Without the strong nuclear force, however, the universe wouldn't exist. And the range of the weak force is still smaller. Thus, we don't directly observe any of these nuclear forces in our daily life. In fact, it was discovered later that the electromagnetic force and the weak nuclear force are one and the same, what we call electro-weak force. Scientists Sheldon Glashow, Abdus Salam and Steven Weinberg, they won the Nobel Prize for this discovery. Even though the electromagnetic force and the weak nuclear force appear to be two different forces now, that is in this place and the time of the universe, they were the same in the early days of the formation of the universe. So we covered all the four fundamental forces. We were talking the classical physics all this while. As we know, both Maxwell's equations and his theory of electromagnetism and Einstein's general relativity theory of gravity are all classical theories like Newton's physics. Now, while these theories accurately explains the phenomena that we encounter in our daily lives and also in the world of bigger objects, including the celestial bodies like planets, stars and galaxies, they fail to explain various phenomena that's happening in the atomic and the subatomic world. These theories don't match with the observations of the tiny microscopic world of atoms, molecules and particles. So if we need to understand the behavior of the atoms and molecules, we need to turn to quantum physics. For example, we would require a quantum version of Maxwell's theory of electromagnetism to understand the phenomena of electromagnetism at the atomic and subatomic levels. Similarly, a quantum version of theory of gravity would be required to understand the early universe when the universe itself was very small. Such theories are called quantum field theories. In 1940, Richard Feynman developed the quantum version of electromagnetic theory. This is called quantum electrodynamics, or QED in short. Similarly, the quantum field theory for the strong nuclear force is called quantum chromodynamics, or QCD. The key difference is, in classical theory, fields transmit force. For example, the magnetic force is transmitted by magnetic fields as described by Faraday. But in quantum theory, the force is transmitted between the interacting objects by exchanging various force-carrying particles called bosons. So there are two types of particles, matter particles and force-carrying particles in the quantum world. Matter particles are called fermions. For example, electrons, quarks, all are fermions. Force particles are those which carry force. Photon, the light particle, is an example of boson, particle carrying electromagnetic force. As per quantum electrodynamics, QED, all interactions between charged particles that experience electromagnetic forces, are described in terms of exchange of photons, the force-carrying particles that carry electromagnetic force. As mentioned earlier, physicists have been trying since long to unify all these fundamental forces, just like how the electrical and magnetic forces were unified, and later how the electromagnetic and weak nuclear forces were unified. Grand unified theory, or GUTs, are grand attempts to unify the strong nuclear force and the electro-weak force, the unification of electromagnetic force and weak nuclear force. But the grand unified theory hasn't been successful in unifying the strong nuclear force and the electro-weak force. So as of now, physics has adopted an ad hoc theory or model, what is called standard model, which comprise of unified theory of electro-weak forces, QCD, the quantum version of the strong nuclear forces. However, these two act separately. The electro-weak force and the QCD, they act separately and are not truly unified. But the standard model is very successful, and it agrees with all the current observational evidences. However, it's still not complete, because not only that it has not unified the electro-weak forces and the strong nuclear forces, it has not included the key component, the gravity. Effort to come up with a standalone quantum theory for the gravity itself has not been successful so far. It's turning out to be a hard problem. Physics, however, is still continuing in the quest of the search for a unified theory, a single force that will unify all the fundamental forces, and thus we'll get one single set of equations that would describe everything happening in the universe, from quarks to galaxies and black holes. It is this journey, seeking to unravel the secrets of the universe that we live in, that makes physics so exciting and mind-blowing. So, thank you for listening in, and I hope you enjoyed the exploration of the force.